What happens when you need Google-level search plus support for wildcards? Design, add, and search words data structure is a Pattern Mastery 100 favorite and a must-know at top tech interviews, blending trie design with recursive search logic. Over 35% of candidates fumble the wildcard or get stuck on recursion. Let's make sure you're ready to shine. Let's break down design, add, and search words data structure using the basic approach, step by step, to cover all the nuances of both trie operations and pattern matching. Build a data structure that supports. Add word adds a word into the data structure. Search word returns true if the word exists. Where can represent any letter. Wildcard input/output supports any lowercase word. Search may include. As a wildcard, needs to handle both standard word lookups and pattern matches efficiently. Imagine a code search tool that must find variables or function names with partial information, like foo.b are matching foobar and foobar. An interviewer might ask, how would you design a dictionary with fast wildcard search for autocomplete or spell checking? What's tricky? Standard trie can handle prefix search, but now you need to support period wildcards, which can match any character at a position. Recursive, DFS, search is required. When you hit period, you must explore all child nodes at that level. Must distinguish between matching a word's full length, is _end, and just matching a prefix. Think step by step. Use a trie node class, children, letter node, and is _end boolean. Add word. Same as regular trie insert, follow/create nodes for each letter. Set is _end at the end. Search, word. Walk down the trie for each character. If current char is not period, follow the child node as usual. If current char is period, recursively try all children at this node. At the end of the word, return true only if the is_end is set. Use recursion to handle branching at period efficiently. Let's clarify. The wildcard search will branch out at each period, but prunes quickly if a child doesn't exist. The structure is the same as a standard trie, but search must explore all possible matching paths when wildcards are present. Edge cases. Multiple wildcards, for example, A, E, empty string, should only match if empty word was added. Search for word longer than any added, should return false trie node. Children, dictionary for each letter is _end, boolean word dictionary. Root node, trie node, add word, standard insert search word, recursive DFS with branching on. Now let's implement the length bucket strategy, grouping words by size so searches only compare against candidates of matching length. We start by defining the word dictionary class. This structure lets us store words and search them, even with wildcards. In the constructor, we create something simple but powerful, a dictionary called buckets. We'll group words by their lengths. This dictionary maps length list of words with that length. This helps optimize wildcard searches later. We define the method to add a new word to our dictionary. This line does two things at once. It ensures there's a list for the word's length. It appends the new word into that list. This way, we always store words grouped by size. This method checks whether a given word, possibly containing dots, exists in the dictionary. Time complexity, on middle.m. Because we compare against all words with the same length, we calculate the length of the input word. This determines which bucket we need to search in. If we don't even have words of this length, there's no chance the word exists, wildcard or not. So we return false. If there is no wildcard in the word, we can do a simple, fast membership check. We return whether the exact word appears in our bucket. No fancy logic needed here. For wildcard searches, we must compare the input word against every stored word of the same length. We begin by assuming the candidate could be a match. We may disprove that shortly. We compare the stored word, A, and the input word, B, character by character. If the input character isn't a dot and it doesn't match the candidate character, then this candidate is not a match. We mark it as not matching, and we break early because there's no point checking the rest. If after all comparisons the match flag is still true, then we found a valid match, return true immediately. And if none of the candidates matched, we return false to indicate the word doesn't exist. And that's how this algorithm works. It first groups words by their lengths, then checks only relevant buckets, comparing letters while respecting wildcards. Efficient, simple, and elegant. Let's check. These operations describe how we interact with our word dictionary. Word dictionary create the data structure. Add word bad, add word dad, add word mad, search pad, search bad, search, add search b. In the bucket by length solution, we group words by their length. So all three words, bad, dad, and mad, go into the same bucket for length 3. Now let's walk through the searches. Search pad, we look into the length 3 bucket. Bad, dad, mad. Compare each character. Pad versus bad P does not equal B, no match. Pad versus dad P does not equal D, no match. Pad versus mad P does not equal M, no match. No word with exact pattern, pad return false. Search bad, same bucket, length 3. Bad versus bad, all characters match, return true. Search add dot is a wildcard that can match any single character. Compare against bad. Dot matches B, A matches A, D matches D, full match, return true. We don't even need to check the rest. Search B, first char must be B, next two can be anything. Compare with bad. B matches B, matches A, matches D, match, return true. Putting all results together. Null, 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 null. False, true, true, true. And that's exactly what we see from the program. Every search behaves as expected. So, our implementation is correct. The bucket by length approach handles exact matches and wildcard patterns correctly by only scanning words of the same length, simple, organized, and working as intended. Now let's implement the trie with DFS, allowing us to explore branching paths and handle wildcard characters smoothly during searches. We begin with a word dictionary class. This structure stores words in a special tree called a trie. This trie lets us search with wildcards efficiently. Our constructor sets up an empty dictionary that will act as the root of our trie. This empty dictionary will grow into a nested tree structure like B, A, T, $, true. Each level represents a character in stored words. This method inserts a new word into the trie, one character at a time. We start at the root of the trie. We walk through each character in the word we're adding. This line does something powerful. If the character key exists, go into it. If it doesn't, create a new dictionary and go into that. This builds the trie branch automatically. We mark the end of the word by storing a special symbol, $. This lets us distinguish full words from prefixes. The search function uses a depth-first search to handle both normal characters and wildcards. Worst-case time complexity. OM middle.26k, because every can branch into all 26 letters. We define a recursive DFS function that matches characters one by one. Node is the current position in the trie. I is the current index in the search word. If we've reached the end of the search word, we return whether this trie node marks a complete word. This prevents treating prefixes like full words. We read the current character we're trying to match. If the character is a wildcard dot, we must try every possible child node at this level. We iterate over each child character in the trie node. For each character branch, except the end marker $, we recursively try to match the rest of the word. If any branch succeeds, we return true. If none of the branches matched, in case of a wildcard, then this path is invalid, return false. For a normal character, if the trie branch doesn't exist, there's no possible match, return false. If the branch exists, continue the search by diving into the next character. Finally, we start the DFS from the root, beginning at index 0. The recursion handles all wildcard and character logic cleanly. And that's how this algorithm works. It first builds a trie structure, then uses depth-first search to explore all matching possibilities, handling wildcards with elegant branching. Efficient, powerful, and elegant. Let's check. In this version, we use a trie where each node represents a character, and we perform DFS when we encounter wildcards. We insert the same 3 words. Bad dad, mad. Each word becomes a path in the trie from the root to an end of word node. Now we run the same series of search calls, but using DFS. Search pads start at root follow P. There is no P child at the first level. We only have B, D, and M. Search fails immediately, return false. Search bad follow B, a D in the trie. We land exactly on a node marked as end of word, return true. Search add at the first character. We branch, try every child of the root, B, D, M. For each path, take B then check add a then D exist as children. We reach an end of word node, return true. Because DFS finds at least one valid path, the search succeeds. Search B, first character B, we go down the B branch. Next character is, so we can go to any child of B, which is A. Next character is another, so from A we go to any child D. We reach the node for bad, which is marked as a word, return true. So, once again, our sequence is null, 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 false, true, true, true. And that's exactly what the program outputs. A perfect match with the expected results. So, our implementation is correct. The trie plus DFS approach fully supports wildcard searches by exploring all possible branches when needed, while still answering all these queries accurately. Wildcard search at Google speed isn't magic, it's design. In this problem, we blended a trie with smart recursion so pattern matches with feel instant and reliable. Let's do a recap. The goal was simple. Build a structure that can add words and search them, where can stand in for any single letter. Conceptually, we're storing shared prefixes once and answering both exact and wildcard queries in OL time. The tricky part is the wildcard. A plain trie handles exact matches and prefixes, but forces branching. We solved this by exploring all children at the wildcard position, while still enforcing that a full word must end at the final node, not just a prefix. We organized everything around a trie node with character links and an is_end flag. The plan: add word walks or creates nodes per character, then marks the end. Search scans character by character. On letters we follow the link, and on. We recursively try each child. Success only counts if we land on a node marked as a complete word. We followed that blueprint exactly. Standard insert for adds, depth first branching on. For searches, and kept the logic tight to avoid unnecessary paths. The solution ran cleanly without errors. We verified on LeetCode. After adding bad, dad, mad, searches like pad returned false, bad returned true, and patterns such as add and b returned true. Edge cases behaved as expected, and tests passed. The takeaway: combine trie sharing for prefixes with precise DFS at wildcard spots. Respect the is_end check, branch only when you see, and you'll get fast, correct pattern matches every time.